Today we will discuss about density of energy states. What is this density of energy states? Just to understand in terms of band, let us you consider this is the potential well. Here I am drawing a set of horizontal lines that indicates the energy levels. If you consider here the electrons are occupying these energy levels. Let us you consider, so n number of such energy levels you can consider. Okay. Now here in each energy level, if I put two dots, means in each energy level 2 electrons can occupy, right? So that means 2 dots correspond to 2 energy states, or you can say 2 quantum energy states, or simply you can tell 2 quantum states. So if I write here, this is the energy level E. Somewhere if I write this one as E plus dE, then what is the interval between E and E plus dE? The interval is dE. So in the energy range dE, the available energy states is, I am writing as G of E into dE. Suppose if dE is equal to 1, that is between E and E plus 1, okay, what is the number of available energy states between the energy levels E and E plus 1? So that means the energy range is unity. In a unit energy range, how many quantum states are available for the occupation of electrons? That is called density of energy states, or DOS. Density of energy state means number of available quantum or energy states per unit energy range. Per unit energy range. That is called density of energy states. See, in case space, just you have studied this one in the last semester. You have constructed a Fermi sphere, right? So here kx, ky, kz. So for free electrons, see, this is the sphere you have constructed. Then to calculate the energy states, what you have to consider is 3 quantum numbers, that is nx, ny and nz. This all 3 quantum numbers, see, they are positive. I am not going to show this mathematically. Okay, just if you take, just you have to divide this sphere into 2 halves. Okay, then the upper half is divided into 8 parts. So that is octant you can consider. So that means I can write this one as like this. Remember, this is 1/8 part of the sphere I have considered. That is the octant I have considered. In this octant, all 3 quantum numbers have positive values. Okay. So that means here nx, ny and nz, they are positive integers only in this octant. Therefore, in my discussion, to calculate the density of energy state, I am considering this octant. Okay. So, this octant is having thickness is equal to dE. This is a dE you have to consider. This octant I am considering with the thickness is equal to dE. That means if this indicates the energy E, then this indicates the energy is equal to E plus dE. First of all, you have to calculate how many energy states are present in the volume enclosed between E and E plus dE, first of all. So, therefore, remember in the simplified diagram I am writing now, just simply you can write Kx, Kz, this is Ky, and you can consider the octant. So, in the momentum space we are marking this. Why? See, you can ask the question, you have plotted Kx, Ky, Kz, then is it the K space? Then how you are saying it is the momentum space? You know, momentum is equal to H cross K. That means if you are saying, if you are marking this one in the K space, it is also true that you can say that this diagram is plotted in the momentum space also. Right. So that means it is Px, Py, Pz. You can think because they are directly proportional. So that means if this is E, this is E plus dE. So in the momentum space, if the momentum of the electron is here P, here it is P plus dP. For our simplicity, what we are considering is, since it is the part of the sphere, right? So, for the evaluation or to get the expression for density of energy state, we can consider the spherical polar coordinate system. So, therefore, now I am writing the volume enclosed between the octant, between E and E plus dE, that means this volume you have to consider. Okay, this volume you have to consider. The volume of that shaded region, I am writing this one as dVp. P represent, we are considering this one in the momentum space. This is equal to, it can be shown that in using spherical polar coordinate system, volume element dVp is equal to P square sin theta into dP into d theta into d phi. So, but you know that momentum P is equal to H cross K, dP is equal to H cross into dK. Now you can substitute here. P square is in the place H cut K whole square sin theta, dP is nothing but H cross into dK into d theta into d phi. So this is equal to, what happens here? H cut square into H cut cube. H cut is nothing but H by 2 pi, right? Therefore, H cube divided by 8 pi cube. 2 pi into 2 pi into 2 pi. 8 pi cube into K square sin theta dk into d theta into d phi. So I am calling this one as equation number 1. Okay. Now, see, in the statistical mechanics, you might have studied, or if not studied, just note this point. Each quantum state occupies the volume is equal to h cube by 2. That means volume per quantum state is equal to h cube by 2. Okay. So that means what? If you consider in the previous diagram, I have just shown one dot that represent the quantum state. That means it is the chair you have reserved for the occupation of electron, right? Then volume of that chair is equal to how much? H cube by 2. That means the volume required for the occupation of the electron is equal to how much? H cube by 2, that much. Okay, so that means, remember, one quantum state requires h cube divided by 2 amount of volume, right? This much of volume. But in our case, what is the volume? dVp. So that means if h cube by 2 correspond to one quantum state, then dVp correspond to how many quantum state, right? So therefore, that means how much? That is dVp divided by h cube by 2. Therefore, I am writing now number of quantum states within volume dVp is dVp divided by h cube divided by 2. So therefore, now you consider the equation number 1. Just rearrange the equation this. So bring h cube by 2 to the left hand side, so that dVp divided by, you bring h cube by 2, here it is 8, right? H cube divided by 2 into 4 pi cube, right? So in which you bring h cube by 2 to the left hand side, that is, it will come to denominator. H cube by 2 is equal to, the remaining term is 1 by 4 pi cube into k square sin theta dk into d theta into d phi. So what is this indicates? Number of quantum states available in the volume dVp. What is this dVp? It is nothing but it is the volume enclosed between E and E plus dE. In other words, you can say that dVp by h cube by 2 is the number of quantum states available in the range E and E plus dE. That is, between E and E plus dV, the available number of states, quantum states, is equal to 1 by 4 pi cube into k square sin theta into dk into d theta into d phi. That means I am writing the number of available quantum states between E and E plus dE as g of E into dE. that is dVp by hq by 2 is equal to g of E into dE. This is equal to 1 by 4 pi cube into k square sin theta dk into d theta into d phi. So this is the equation number 2. This is equation number 2. Okay. So therefore, how you can get the expression for density of energy state? This is number of available energy states between E and E plus D. Density of energy state is, it is per unit energy range, right? dE is very small interval. Therefore, the unit energy range here, if it is E, this is E plus 1. This is divided into n number of intervals. Each interval is equal to dE. That means you have to add the available energy states in n intervals. If the interval is very short, then what we have to do? You have to go for integration with respect to the theta and phi, right? So therefore, in order to evaluate the density of energy state, what we have to do? You have to integrate the equation number 2. That gives the total number of available energy states between E and E plus 1. Therefore, density of energy state is equal to G of E. This is equal to integration, double integration, because theta and phi we are considering. So therefore G of E into dE. So substitute the value. This is equal to 1 divided by 4 pi cube integration k square sin theta into d theta into d phi divided by, what I am writing is this one. Okay, just sorry, it is k square sin theta d phi into dk. So now this is equal to 1 by 4 pi cube, okay, integration k square sin theta into d theta d phi into dk divided by dE into dE. So this can be written as, therefore G of E is equal to 1 by 4 pi cube integration k square sin theta into dE into d theta into d phi right. Divided by dE by dk. Okay, divided by dE by dk. This is what you have to get. So just recall this, right? So this is what you are getting now. G of, just see here, 2 d theta into this, stop. Okay, now here actually we are, when you come into this dE, in this is the range we are interested. That means density of energy state is for unit energy range. Therefore, in the next step, I am reducing that dE to unity. Therefore, it becomes 1 by 4 pi cube integration k square sin theta into d theta into d phi divided by dE by dk. So this is the equation number 3. So now what we do is, to understand this, for our simplicity, let us we consider the simple cubic system. Simple cubic system. So you have this expression. Already we have come across this expression in the tight binding approximation discussion. E of k is equal to E naught minus alpha minus 2 beta into cos kxa plus cos kya plus cos kza. So now let us we consider the case near the bottom of the band, right? So that means kxa is much less than 1. Similarly, kya is much less than 1. Kza is much less than 1. Under this approximation, you can write in general cos ka is equal to 1 minus k square a square divided by 2 factorial and so on, right? So therefore, neglecting the higher order terms, apply this and simplify the equation. E of k is equal to E naught minus alpha minus 2 beta 1 minus kx square a square divided by 2 plus 1 minus ky square a square divided by 2 plus 1 minus kz square a square by 2. Right. So therefore here of next step it becomes E naught minus alpha 1 plus 1 plus 1 3 into minus 2 beta minus 6 beta, then multiply this minus 2 get cancelled, remaining is what you have, beta a square into kx square. Similarly, in the next step you have minus beta a square into ky square minus beta a square into kz square. So therefore minus into minus it becomes plus. Beta a square is the common term, take outside the bracket, remaining is kx square plus ky square plus kz square, right? So therefore in general you can write E of k is equal to, I am writing these are all constant, right? E naught minus alpha minus 6 beta as E1 plus beta a square. What is kx square plus ky square plus kz square? That is nothing but k square, right? K square, that is the thing. Now you differentiate this equation with respect to k, dE by dk. This is equal to, differentiation of this is 0, remaining is beta a square, differentiation of k square is 2k. That means 2 beta a square into k. That is the value of dE by dk. Okay. So now you substitute this. Okay. Now G of E is equal to 1 by 4 pi cube into k square divided by dE by dk. So we are integrating between theta and phi only, therefore you can take outside the integration sign. So phi varies between 0 to 2 pi, theta varies from 0 to pi. So sin theta d theta into d phi. So now integrate this. So this is equal to 1 by 4 pi cube k square into dE by dk into, see here, the integration of sin theta is minus cos theta, limit from 0 to pi, right, minus into cos pi minus cos 0, minus 1 minus 1 minus 2, minus 2 into minus plus 2, right. So therefore you can write, so integration of sin theta d theta with the limit 0 to pi is 2. Integration of d phi is phi, upper limit is 2 pi, lower limit is 0, therefore it is 2 pi. So this is equal to 1 by 4 pi cube into k square. See, dE by dk, right? That one you have to substitute. That is equal to 2 beta a square k, 2 beta a square k into 4 pi, right? So what you are getting now? This is equal to 1k get cancelled, remaining is k divided by 1 pi get cancelled, 4 get cancelled, right? You are getting 2 pi square, right, beta into a square, right? So k divided by 2 pi square beta into a square, that is g of E you are getting now. So now what is the next step? Just recall the equation. E is equal to E1 plus beta a square k, beta a square k square, right? Recall this equation, rearrange it for k square. So just before we have written this, right? So therefore k square is equal to E minus E1 divided by beta into a square, beta into a square, right? So or k is equal to square root of this. So therefore square root of E minus E1 divided by beta a square, right? So therefore substitute here, just g of E is equal to, so in the place of this you have to substitute, right, k, k value you can substitute. So what you are getting, I am writing this square root of E minus E1 divided by beta a square to 1 divided by remaining terms 2 pi square beta a square. This is equal to square root of E minus E1 divided by 2 pi square beta a square to the power 1, beta a square to the power half, it becomes beta a square to the power 3 by 2. That is equation number 6. Okay. Now, we know that effective mass m star is equal to h cut square divided by 2 beta a square. from this you can write beta A square is equal to h cut square divided by 2 into m star. Right. So now you have to substitute the value of beta A square in the expression for G of E. Okay. So therefore G of E is equal to, right, square root of E minus E1 divided by 2 pi square into beta A square. Beta A square is nothing but h cut square divided by 2m star to the power 3 by 2. Right. So now you can simplify this. Right. This is equal to, so square root of E minus E1, then here 2m star to the power 3 by 2 comes to numerator divided by 2 pi square into h cut cube. Right. So here what happens now? This becomes h cut cube. Means what? H cut cube means h cube divided by 8 pi cube, right? So h cube divided by 8 pi cube. Therefore, in the denominator what remains? See, I am replacing h cut cube by h cube divided by 8 pi cube. So here what happens now? Pi square get cancelled. Remaining is 8 pi. Right? 8 pi comes to numerator. See, 2 to the power 3 by 2 divided by 2. That is 2 to the power 3 by 2 minus 1. That is, what happens? 1.5 minus 1. Half remains. That is 8 root 2 pi. That comes here. Into m star to the power 3 by 2 into square root of E minus E1 divided by h cube. This is the expression for density of energy state near the bottom of the energy band. In the previous semester you have considered that is in metals, not according to the band theory, according to the quantum free electron theory. You have deduced the expression for density of energy state. This is the available energy states near the bottom of the given energy band. How many available energy states at the bottom of the band in the unit energy range? That is given by this expression. So from this you can observe that if you plot a graph connecting density of energy state versus E, what you will get? See, that is nothing but y is equal to a into x to the power half. That is nothing but equation of a parabola. That means parabolic free electron density states with inertial mass is replaced by the effective mass, right? So what you are observing is parabolic nature we are observing, but the inertial mass is not present. It is, we are replacing it with the effective mass. So that is the thing. Similarly, now let us consider at the top of the energy band, though I am writing that one as E of k dash, just only to differentiate. The expression is equal to, this is, we have not reduced, just to remember this expression, E naught minus alpha plus 2 beta into cos kx dash a plus cos ky dash a plus cos kz dash a. Right. So finally, for small values of k dash, we can write, it can be simplified as E naught minus alpha plus 6 beta minus beta a square into k dash square. In your mind, keep this one as k square only. Only in the previous case, we have taken k for bottom. Therefore, here also same k, but it is at the top. Remember. So, this is equal to E naught minus beta a square k dash square. So now if you differentiate this, dE by dk is equal to, when you differentiate it, so you can dk dash, doesn't matter, dE by dk dash is equal to minus 2 beta a square into k dash. Similarly, here m star is equal to minus h cut square divided by 2 beta a square. Remember, effective mass may be positive or negative. It can be shown at the top of the band. Its expression is minus h cut square divided by 2 beta a square. We have not studied. So, you follow the same procedure as earlier. Okay, same procedure. And simplify the expression, substitute in the expression of g of e and follow all these procedures. Finally, you will get g of, this is homework for you, the simplification part, identical to this. Okay, so it is 8 root 2 pi divided by h cube into m star to the power 3 by 2 into square root of E1 plus 12 beta minus E. This is finally, you will get it. Okay. So, this is the expression for density of energy states at the top of the energy band. So, now, just we have to plot the graph, right? So, here also we are observing the parabolic nature. So, that means if you plot a graph connecting g of e versus E minus E1, then you are observing a parabolic variation up to 4 beta. Similarly, up to 12 beta, see, you are observing in the negative way, right? It is also the parabolic nature only. So, this is at 12 beta. This one variation is observing up to 8 beta, just the qualitative. Between you have this. So, that means this is the at the bottom of the energy band. This is the variation we are observing at the top of the energy band. This is in between. Almost the density of energy state remains almost the same at between 4 beta and 8 beta. But if the bands are overlapped, say for example D band and S band get overlapped, in that case just I am mentioning the expression, sorry, graph for G of E versus E is, you will get of this kind. Okay, so one, this is for D band, this is for S band. So how the density of, if the overlapping of bands takes place, then the density of energy state graph comes to be like this. We have not discussed the equation corresponding to this. This is about density of energy states.